Good. So, as you'll recall from last time, I guess would have been Wednesday when we were last talking about class material, and boy, it's really getting down to the wire, isn't it? If I'm not wrong, a week from today is our last class. I've also heard from my previous class, and I think you guys can confirm this. They told me that there is no lab this week because your lab final is this week, which I hope and pray goes better than last term. Last term, the system just died from all of everyone logging on all at once, and it was a huge to do. I have nothing personally to do with the administration or grading of the lab exam, even if I'm your professor of record. But please know that I will be fingers crossed, thumbs, big toes, etc., crossed the entire time that you guys are taking it. I'll be thinking of you. I just hope it goes more smoothly than last term. It literally could not possibly go worse than it did last term. So we'll hope for the best. But anyway, when we were discussing class material last, we were talking about reduction of aldehydes and ketones in order to make alcohols. And that's a logical thing that belongs in this chapter. The chapter is about alcohols, so it's perfectly reasonable to cover methods of making alcohols. And we saw that we already knew some, even though we may not have been thinking of it in those terms, we already knew some methods of making alcohols, like hydration of alkenes, for instance. Uh, but we also said that you can reduce aldehydes and ketones. And in that case, we have two reagents that will do the job for us, lithium aluminum hydride and sodium borohydride, that as far as aldehydes and ketones go, these two reagents are interchangeable. It doesn't matter which you use, you'll get the same result. So a ketone will get reduced to a secondary alcohol and an aldehyde to a primary alcohol. And there will never be any exceptions with either of those cases. So do recall what it is that you have to put down. Remember that LAH is more reactive, and so we need to keep it away from protic species in order for it to be able to do its work. So that's why we need to first do the reaction in an aprotic solvent, usually an ether. Diethyl ether is fine, THF is fine. You know the drill. Methyl tert-butyl ether is fine. 1,4-dioxane is fine. 1,2-dimethoxyethane is fine. You get the point. Any ether solvent is fine. And then we need to do a workup step. So this will be, you can put either dilute acid, dilute aqueous acid like this, or just H2O. Either one will do the job for us. And let's not forget the point of a workup step, something we've said before, but bears repeating. That the point of a workup step is twofold. First of all, if there's any excess nasty reagent, we need to destroy it. We need to neutralize it so that we can safely isolate our product. And certainly that's the case with LAH. Very nasty. We need to be sure that we neutralize it. Reacting that with water will give us lithium salts, probably lithium hydroxide, and alumina, which is essentially aluminum with 3 OHs on it. That's very benign and neutral and is almost like a kind of sand, a little bit soluble in water. So both of those can be removed from removed just doing an aqueous organic extraction, and then we can isolate our product alcohol safely. Let me write this bigger so that it's easier to read. Should really remember to write bigger in general. So we're talking about LAH right now. So we need that workup step in order to kill off the excess LAH, which you would want to use in excess. Another reason that we do workup steps of this type is if we wind up with an ionic intermediate, and that's going to be the case here. You're not responsible for the mechanisms of these reactions yet. We will get to them next term, probably in chapter 19. But when we do, you'll find that you get essentially the conjugate base of this species at first. You get O minus. And we can't isolate that. It's not practical to isolate ions. We only want to isolate neutral compounds, very much easier. So, so we need to put that proton back on. And that's the other function of adding water or dilute aqueous acid. We want to be sure that we can get a neutral product out at the end. So you need to know that so you can remember when and why you want to use workup steps. And so that's why we'll generally want to introduce something that's the chemical opposite of the main reagent. And in this case, this is the source of H minus, so is this. And so H minus is a really strong base, so we need a weak acid, and either dilute aqueous acid or just water will do the job for us. So in contrast, with sodium borohydride, you can usually do that with just one step. It's not wrong to put this as the first step and then 2H3O plus. That's fine. You can do an acid workup step. I think it's just in general not necessary. You'll find out probably next term, I believe you're going to do a borohydride reduction, those of you who take Organic 2 lab. And we'll see if you do a workup step. The way we used to do it at my previous school is we would just heat it up at the end, just get it to boiling. And that would make the reaction of any leftover sodium borohydride with the alcohol and water very much faster. Sodium borohydride does react with these product solvents, but very much more slowly than it reacts with the carbonyl group. So that's why you can get away with using a product solvent here, whereas you couldn't with LAH. That would just be violently reactive. But if instead we just heat this up, that makes that reaction much faster, and you can essentially get rid of the excess sodium borohydride that way. And that will also put the proton back on. So it's important to understand the difference between the reactivity here, although in terms of the outcome with aldehydes and ketones, it's the same. Those two reagents are interchangeable. We're very shortly going to get into a situation where they're not interchangeable. But before we do that, I do just want to point out that reduction reactions of this type are very, very common in biological systems. Next term, we'll do a chapter on, what's the word I'm looking for? Metabolism from the perspective of an organic chemist. And you'll see plenty of reduction reactions of that type in glycolysis, the Krebs cycle, things like that. Only, of course, we don't keep lithium aluminum hydride or sodium borohydride in our bodies, and neither does any other living creature. Instead, we have biological reducing agents that do that for us. You probably have heard of them in your biology classes. They're species like NADH, the nicotinamide dinucleotide in the reduced form, and NADPH. So those are essentially biological LAH. So like I said, these two reagents are interchangeable for as far as aldehydes and ketones go, but not for carboxylic acids and esters. So that's where we're going to turn our attention next. And what we're going to find is, let's even write it down. For ketones and aldehydes, lithium aluminum hydride and sodium borohydride are interchangeable. Doesn't matter what you use, same result. They will reduce, both of them, a ketone to a secondary alcohol and an aldehyde to a primary alcohol. And it's good to have reagents that are interchangeable, by the way. Because what if you're, in the lab in industry somewhere and you try one of them and it doesn't work for some reason? Then you have another option. But however, for esters and carboxylic acids, now they are not interchangeable any longer. Carboxylic acids. And what we find here is LAH reacts with these functional groups, but sodium borohydride does not. And we'll do examples of both those kinds of reactions in just a moment. First, I want to get down for you kind of the general case, which is that we can take, I'm going to use R1, and you'll see why in a moment. We can take any carboxylic acid or any ester, OR2, let's say, our choice of either of the above, and we can react this with LAH. Same deal as before. We want to use diethyl ether or some aprotic solvent for that first phase of the reaction. Then we will do our workup. And you can write here either H3O plus or just water. Both of them will successfully work up the reaction. And in the end, the major organic product that we will get is the corresponding primary alcohol. By corresponding, I mean that it is the same number of carbons in it. So this CH2 carbon here used to be the carbonyl carbon in either the ester or the carboxylic acid. If we're using an ester, this R2 group is going to wind up in a molecule of R2OH, which 99% of the time that's going to be either methanol or ethanol. Both of those are soluble with water in all proportions. So when you do your aqueous organic extraction, that will wind up in the aqueous layer and be separated from the product that you want to isolate, which is going to be this primary alcohol. And there are other inorganic side products as well. Of course, you'd get aluminum salts, you'd get lithium salts. But the major organic product, the one we're concerned about, is this primary alcohol. And that's what you will get from either a carboxylic acid or an ester. And just as before, you're not responsible for the mechanism yet. We will eventually get to it next term. And that's going to be true for the other things we discussed today as well. So lithium aluminum hydride will do this type of transformation for us. Sodium borohydride will not. Sodium borohydride does not react with either carboxylic acids or esters. The most you'd get from carboxylic acids is the H minus in sodium borohydride will deprotonate your carboxylic acid and give you a carboxylate ion, but that's it. You will not get any reaction with the carbonyl group. So sodium borohydride does not touch carboxylic acids or esters. It will only react with aldehydes and ketones. And what that means is that you can take advantage of that reactivity. But before we go there, let's do at least some examples of this type of reaction. Let's look at, I want to at least give you one example. Oh, I don't know. Let's do, since we've already given examples of this type of reaction, let's do, oh golly, I don't know. Ethyl hexanoate. 2, 3, 4, 5, 6. Right, and you can abbreviate esters like this. That means C double bond O, O ethyl. And so if we were to treat this with LAH, diethyl ether, THF, whatever you like, and then an aqueous or aqueous acid workup, you would get 1 hexanol out of this. 4, 5, 6. OH. So it should have the same number of carbons as the starting material. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. Yep, we're good. And of course, you'll get ethanol as well. That will wind up in the waste jug. So that's just an example of this type of reaction. And if instead of this ester, you just had hexanoic acid, the corresponding carboxylic acid, well, then you would get the same compound out at the end. But sodium borohydride will not touch esters or carboxylic acids. And you can take advantage of this, actually, this difference in reactivity. Let's say that we altered this compound slightly so that in the other end, we had an aldehyde functional group. Just as an example. Well, if we treated this with lithium aluminum hydride, it would hit both those functional groups. And yes, generally we do use an excess of LAH, not to mention, by the way, that even if you use just one equivalent, you've essentially got 4 equivalents of H minus. Same thing for sodium borohydride. So you've generally got an excess of the hydride ion built in to this reaction. And then we'll do an aqueous or aqueous acid workup. I would expect that both of those functional groups would get reduced, and there would be a total of 1, 2, 3, 4, 5, 6, 7 carbons. 1, 2, 3, 4, 5, 6, 7. So you'll get, why don't we call that 1,7-heptane diol? How does that sound? I'm happy with that name. And yes, there's no doubt someone somewhere that will say heptane 1,7-diol. Fine. I'm okay with that. Either way, that sounds fantastic. Why is the second step H2O instead of H3O plus? Because I'm trying to show you that you can put either. Both are correct. Both are acceptable. So I'm just trying to get you guys used to the different things that are equivalent sort of responses. But now let's say that we took this same compound and instead reacted it with sodium borohydride. And by the way, this could be either, I'll do it again, this can be either methanol or ethanol in water. Either is fine. Those are the two most commonly used. Those are the ones that you can most easily get your hands on. But in this case, I would expect that the sodium borohydride will reduce the aldehyde, but it will not touch the ester. So the compound I'd expect you to get, 1, 2, 3, 4, 5, 6, 7, would be that one. So the ester will not be reduced, only the aldehyde. So that shows you the difference in reactivity. And what would I call that? Oh, goodness knows. We'll worry about learning how to name esters next term when we cover carbonyl compounds in some depth. And so that's why, like I said, we're not doing the mechanisms now. You're not responsible for the mechanisms yet. We'll get to the mechanisms next term, probably in chapter 19. Good. So that was one point I wanted to make about sodium borohydride versus lithium aluminum hydride. They are interchangeable as regards ketones and aldehydes, but not for esters and carboxylic acids. Then they're no longer interchangeable. Good. Any questions so far then? All right, since I seem to have done it again, let's up the ante a little bit. We've seen how to form new carbon-hydrogen bonds at carbonyl carbons. And that's fine. That certainly had its place. It must, or as I said, we wouldn't have biological equivalents like NADH. But how about forming new carbon-carbon bonds at a carbonyl carbon? That's going to be something even more useful, since a point I've made repeatedly in the past is anytime you can form a new carbon-carbon bond, then you're converting a simpler compound to a more complicated compound. And as far as the pharmaceutical and other synthesis industries go, that's money in the bank. Anytime you can form a new carbon-carbon bond. Very, very important in any field that touches on organic synthesis. And the reason that we can do reactions like this on any carbonyl group is the same as the reason that we can form new carbon hydrogen bonds there. So not only new carbon-carbon bonds, but new carbon hydrogen bonds. And the reason behind that is the same in both cases. Just a moment. It's a little better. And that is that carbonyl groups, regardless of whether it's an aldehyde or a ketone or a carboxylic acid or whatever, carbonyl groups are resonance stabilized species. And so, again, I say this as always for myself as well as for you guys. Remember, it's not an equilibrium. It's not two different species flipping back and forth. There's one species that is at all times a hybrid, a mixture of those two structures. And surely this is going to be the major contributor by far. But the existence of this minor contributor does matter. It means that the carbonyl carbon has a partial plus charge on it. And there's other reasons for that as well. You could talk about oxygen being so much more electronegative than carbon, sucking electron density away. Sure, that's certainly true also. More things that we'll get into in more detail next term. But even now, we can have some understanding as to why there's a partial plus charge on that carbon. And when we say there's a partial plus charge on that carbon, What we're saying is that carbonyl groups tend to react as electrophiles. They tend to react with nucleophiles, like H-, small wonder that sodium borohydride and lithium aluminum hydride react with carbonyl groups. And by the way, welcome to organic chemistry too. Carbonyl chemistry is always dominant in organic chemistry too. If I had to guess, probably at a conservative estimate, 60–65% of what we'll be discussing next term is going to involve the chemistry of carbonyl groups showing up in various different functional groups. So it's a really dominant feature of organic chemistry too, anywhere, at any school. It was the same at my previous school, it'd be the same wherever you went, probably not just in this country, but around the world. Good, so what that means is that we can treat carbonyl-containing compounds of various functional groups with nucleophiles of all kinds. And one nucleophile we learned about in chapter 10 is organometallic species, in particular organolithiums and Grignard reagents. We said that you could take pretty much any alkyl halide you like and react this with magnesium metal in a polar aprotic solvent such as diethyl ether, and you will get the corresponding Grignard reagent. The magnesium inserts into the carbon metal bond. We also said that you can take an excess of lithium metal. You'll need at least two equivalents, so you can write either two lithiums or excess lithium. Here you'll need some, certainly aprotic species, something that's not going to react with the carbon metal bond. You can use an alkane like pentane or hexane. You could also use diethyl ether. That's fine also. And you will get, that's an Li, you will get the corresponding organolithium plus other inorganic species. You would get like the lithium halide salt. And we talked about that. If you've forgotten about those reactions, please review them. I think they're in 10.6. Let me just confirm that for you. Yep. So we talked about those reagents back then. And we said back then that, first of all, organolithiums and Grignard reagents are interchangeable. They have essentially identical reactivity. And we also learned one reaction of these species back then, which is, if anything, a pretty useless reaction. We said you can treat alkylithiums and Grignard reagents with protic species, water, alcohols, carboxylic acids, primary and secondary amines, et cetera, et cetera. And you will convert the carbon metal bond in both cases to a carbon hydrogen bond. Why doesn't the halogen stay with lithium like it does magnesium? Good question, because lithium can only form one bond, right? Magnesium forms two bonds. It has 4 electrons around it. Both of them are exceptions to the octet rule, but lithium can form only one bond. Magnesium forms 2 bonds. So that's the reason why. That's why the halogen will show up in lithium chloride, lithium bromide, or lithium iodide as an inorganic side product. So good to review these reactions. So these are perfectly good questions, perfectly valid questions. In any case, the reactivity of these two species is interchangeable. But we only learned that they could be protonated with protic species. These two types of species also both react with carbonyl compounds of any type. And we'll do the general forms first. I want to get down the general forms or the generalizations, if you will, and then we'll look at some specific examples. First of all, if you took an aldehyde or a ketone, so this is an aldehyde or a ketone, and you treated it with either an alkyl lithium or a Grignard reagent. Let's say R3 lithium or R3 MgX. It's an M, but it looks like an H. In some unreactive solvent like diethyl ether. And then again, we're going to need to do an aqueous workup. Here you could put, again, either H3O plus or simply H2O. I have no preference. Both of them are perfectly acceptable. Either of them might be done at times, depending on the specifics of the organometallic reagent. And in the end, the major organic product that you will get will be either a secondary alcohol or a tertiary alcohol, depending on whether you started with a ketone or an aldehyde. And it would have this general structure. And don't worry, we'll do at least one example of this. And there's inorganic side products also, of course. You would get magnesium or lithium salts, but certainly the major organic product, the one you're going to isolate, is going to be an alcohol of this type, either a secondary alcohol if the starting material is an aldehyde, or a tertiary alcohol if the starting material is a ketone. But either an aldehyde or a ketone will react with either an alkyl lithium or a Grignard reagent to give you an alcohol of this type. And it makes sense to mention this reaction in this chapter, since this chapter is about alcohols. This is another way of making alcohols, and not only making alcohols, but alcohols in which we formed a new carbon-carbon bond. So we can get a more complicated structure from a less complicated structure. Esters indeed also react with either alkyl lithiums or Grignard reagents. I'm going to go OR2 for kind of a generalized ester. In this case, as you're going to see, we're going to need an excess of the alkyl lithium or the Grignard reagent. You're going to need at least 2 equivalents, so you can just use a 2 like this or write excess. Either way is fine. But either 2 alkyl lithiums or at least 2 equivalents of the Grignard reagent. And again, using some kind of inert solvent like diethyl ether would be fine. And again, you need either dilute aqueous acid or just water as a workup step. But you can write either H3O plus or H2O. Either one is fine. You may be given either one of those, just so that you're ready for the different variations you might run into. And in the end, the major organic product that we're going to get is going to be a tertiary alcohol in which we've incorporated 2 of these R3 groups. That's why you need an excess. And you will get an alcohol of this type. The group OR2 is going to wind up in a small alcohol molecule, R2OH. 98+% of the time, that will be either methanol or ethanol, since most of the esters we use in organic synthesis are going to be either methyl esters or ethyl esters. So nearly always it's going to be one of those 2. Both of those alcohols are soluble with water in all proportions. They'll go into the aqueous layer when you do your aqueous organic extraction, and thus into the waste jug, along with any other inorganic salts like lithium or magnesium salts. But the major organic product you get will always be a tertiary alcohol of this type, with both of those R3 groups incorporated into the molecule. And we'll do some examples of both of these, don't worry. In fact, so basically the point of this is something else you can do with Grignard reagents and alkyl lithium, something much more useful than just replacing the carbon-metal bond with a carbon-hydrogen bond. You can make a new carbon-carbon bond there. So for example, let's just say, and again, we'll learn those mechanisms next term. You're not responsible for the mechanisms yet. We'll get to that next term. Let's say that we took stereotypical ketones, such as, I don't know, how about 2-pentanone? And we'll learn how to name ketones and aldehydes next term. But I think if I told you that that one is called 2-pentanone, exactly 0 of you would be surprised by that. Pentane, because there's 5 carbons, one for the ketone, 2 because it's in carbon 2, 2-pentanone. Very logical. That's why I always say, if you can name alkanes and cycloalkanes, you've got at least 90% of what you need to know to name anything, maybe even more. Let's say that we treated this guy with, I don't know, phenylmagnesium bromide. Can I go pH MgBr for phenylmagnesium bromide? pH, of course, meaning a benzene ring. You could draw it out also. Or if you don't like pH, you can write C6H5. Perfectly fine. Not only will I not take off points, I won't even notice. And again, we want some inert solvents such as diethyl ether. THF would also be fine. And then we did an aqueous or aqueous acid workup. I'll just write H2O here just so you guys get used to seeing that as well. And what I would expect to get out of this is, in this case, a mixture of two different tertiary alcohols. One of them would look like this, and you would also get the enantiomer. So the phrasing of the question will tell you what you need to put down as the answer. Of course, lots of times, OWL will just say, don't even worry about stereochemistry, in which case don't even bother with wedges and dots. But I think you can see we do generate a chiral center here, right? This carbon is 4 different groups: methyl, propyl, phenyl, and OH. So we've generated a chiral carbon. And in those cases where we need to account for stereochemistry, we would need to say that. But there wouldn't be any reason that I would expect you'd get one over the other. So I would expect that you'd get a racemic mixture. And again, the question will tell you to draw both or to draw just one of the enantiomers, or don't even worry about stereochemistry. So that's how you know which to put in response to that. So that's one example. What if we took instead an ester? Like, oh, I don't know, ethyl benzoate. And let's say we treated this with an excess of butyllithium, Bu for butyl group. So this is CH3, CH2, CH2, CH2 lithium, which is very easy to get. Let me just make that lithium look a little neater. In fact, you can buy it in solution in hexane. But you could use pentane if you wanted. You could use diethyl ether if you wanted, just as long as it's a solvent that doesn't react with organometallic reagents. And then we did either a dilute acid workup or just water as a workup. Well, in this case, what I would predict we would get would have, oh, right. Why am I losing my mind here? We'd have an OH group, of course, and we'd have 2 butyl groups attached. So however you wish to draw that, looking something like that. And actually, look, in this case, lo and behold, that carbon is not chiral. It is 2 butyl groups attached. So I'm just showing you how chirality is not something you memorize and bring into the problem beforehand. You need to judge each separate case on its own merits in terms of what you need to show. Here, when I look at what I've just drawn, lo and behold, that carbon's not chiral. So there's no stereochemical issue, just straight lines are fine. But that's the compound that I would expect to get out at the end, this tertiary alcohol. So that's how, and again, if we'd used a Grignard reagent here, same type of thing would happen. Likewise, if this were phenyllithium instead of phenyl magnesium bromide, same thing would happen. Don't forget also that it's not always MgBr, right? That can also be a chlorine or iodine. Those are also fine. So these are some examples of how certain representative carbonyl compounds react with alkylithiums and Grignard reagents. Ketones and aldehydes undergo one addition. So of course that phenyl group comes from the organometallic reagent. Esters actually undergo 2 additions. But what about carboxylic acids? You'll have noticed that I didn't mention carboxylic acids. And that's because carboxylic acids, we already know, do not react with either alkylithiums or Grignard reagents in this kind of addition reaction. Instead, they protonate it, right? Because carboxylic acids are protic species, right? There's your labile proton, your acidic proton. So it doesn't matter what R is if you treat either a Grignard reagent or an alkylithium with any carboxylic acid, regardless of what R is, you're not going to get this kind of addition reaction. All that will happen is the proton and the carboxylic acid will take the place of the metal. You'll go from a carbon-metal bond to a carbon-hydrogen bond. And so that's why if you treat any carboxylic acid with either an alkylithium or a Grignard reagent, all it will do is pull off the proton and then you're done. It's not going to react further. But esters don't have that proton. And so they will react as expected. Which gets us into one last topic that I'd like to get to today, which is this whole idea of incompatible functional groups, and then the idea of protecting groups. So, and I think that will be plenty for today, if we can get that far. Good. Any questions on the reaction of either esters or ketones or aldehydes? Why isn't the butyllithium reacted in? Oh, I forgot. You're quite right. You do need an excess of butyllithium. I'm sorry about that. You do need two equivalents. Good catch. And again, you can write either excess butyllithium or 2-butyllithium. And if you don't like Bu for the butyl group, you can just write CH3, CH2, CH2, CH2Li or Li. If you want to just do line angle drawing. Yes. Oh, you're fine? Okay. Just stretching. Good. Thank you for that. Yes, I did miss that. Good. So this brings up a topic that's somewhat subtle, which is the idea that ketone, an aldehyde, an ester, and carboxylic acid and alcohol, and I'll write all these down, don't worry. All these other product groups that we discussed in chapter 10, these things cannot exist in the same molecule as a carbon lithium or carbon magnesium bond. So what we learned in chapter 10 is that alcohols, what else? What about carboxylic acids, like we just said? What about primary and secondary amines? So I'll just leave those other two bonds unspecified. They can be to either hydrogens or carbons, but at least primary or secondary amines with at least one NH bond in there. Am I forgetting anything with an OH? I don't think so. I mean, thiols, I guess, RSH. They're not something you run into very often, but anything like that that has labile protons, something that can be pulled off, one that can be pulled off by a strong base, any slightly acidic compound, these cannot exist in the same molecule as a carbon lithium or carbon magnesium bond. And we also just learned that not only those, but also ketones and aldehydes, and also ester functional groups. Oops, OR2. So all of those functional groups, we would say these cannot exist in the same molecule as a carbon lithium or carbon magnesium bond. Or in other words, one word that you'll hear used quite a bit is we say these groups are incompatible with carbon lithium or carbon magnesium bonds. You can put it either way. And hopefully the reason for that is fairly clear. What that means is, just to give an example, let's say that we had some molecule that looked something like this. We've got a carbon-bromine bond here, and we're hoping to insert magnesium in there. And we're hoping to get something that looks like this. This reaction will fail. You're not going to be able to get that compound because you've got a reactive carbon metal bond that reacts with ketones. And so you're not going to get a stable organometallic species out of that. Either this compound just flat out won't react with magnesium, or if it does, it'll immediately kill itself, essentially, because you've got a carbon metal bond that will react with another functional group in the molecule. Either way, you will not get this. Or to give another example, what if, let's take a benzyl alcohol derivative, and let's put an iodine over here. Let's say we're hoping to get the corresponding alkyl lithium. And what we're hoping to get would look something like this. Again, that reaction will fail. You won't be able to get this alkyl lithium because there's a protic functional group here that reacts with alkyl lithiums. So either this just won't react in the first place with lithium, which is entirely possible. The lithium can just reduce the hydrogen in the alcohol, and you'll get O- and H2, 1/2 H2. But even if it does react, that will immediately destroy itself. So you cannot have organometallic reagents if there's a functional group in the molecule that would react with an organometallic reagent. That's basically what this whole idea here is talking about. Those two functional groups cannot coexist in the same molecule. They are incompatible. You cannot have an organometallic reagent if there's also a functional group elsewhere in the molecule that reacts with organometallic reagents. That's basically the idea we're trying to say here. And it's kind of a subtle idea, but we need to bring that up. And that brings up what I think is going to be our last topic for today, which is there anything you can do about that? Is there any way that you can get around a problem like this? And the answer is yes, you can. You can do it by protecting the incompatible functional group, or by putting on what's called a protecting group. And we'll end with an example of that. So let's say that for whatever reason, I'm some lab worker in Eli Lilly or whatever pharmaceutical company you want, and I need to make an organometallic. I need to make an alkyl lithium or a Grignard reagent in that carbon iodine bond. The way I would go about it, my what's the word I'm looking for? Strategy would be to protect the alcohol so that there's no longer an alcohol functional group that can react with the carbon metal bond. Then I install my carbon metal bond and do whatever chemistry I want. And then I deprotect my alcohol. I remove the protecting group. And there are scads of different protecting groups. We'll learn next term it's also possible to protect ketones and aldehydes. So, and there's many other ways of protecting alcohols than just the one I'm going to show you today. But one very common way of protecting alcohols is by converting them to what's called a silyl ether. And so maybe we'll do that first. And one of the more common types of silyl ethers is a trimethylsilal ether. And the way we put one of those in is using chlorotrimethylsilane. So we get to use silicon today. And we'll learn more about mechanisms of reactions of this type next term, but I think for now it's good enough to say it's basically kind of like it's an SN2 reaction. I think you can see that we've got an electron-rich alcohol oxygen that can, if you will, attack the silicon and kick out the chloride ion in some sense. We also, in addition, are going to need some base. Pyridine is fine. Triethylamine is fine, because I think you can see we're going to get the equivalent of HCl, because the proton and the oxygen and the chlorine on the silyl chloride are going to come together and make HCl. So we need some base to mop that up for us. And triethylamine is very common. There are others. You can use, there's one with isopropyls. I'm trying to remember what it is. Anyway, but probably some tertiary amine is going to be used in that case. And what you will get out of this is this trimethylsilal ether. And again, I think you can see that's just a substitution reaction. The mechanism is probably sort of kind of like an SN2 reaction. That at least will get us into next term when we can talk about things like this more in detail. But now we can go ahead and make our alkyl lithium or Grignard reagent. So we'll take at least two equivalents of lithium metal. This is Li. Let me try that again. In hexane or pentane or diethyl ether or whatever solvent you like. And now we can actually get that organolithium reagent. This compound now can exist. We've taken away the incompatible functional group. And so that now is a thing. That's a compound that can exist. We can now, let me move you guys over here. We can now go ahead and do whatever chemistry. Let's say we wanted to treat this with, I don't know, how about 3-pentanone? Just because it came into my head, and maybe for one other reason that we'll get to in a second. And of course, we'll need some kind of aqueous workup, either water or dilute acid H3O+. And now we're going to form a new carbon-carbon bond here. We're going to form a bond between that carbon that bears the lithium and the carbonyl carbon. And so I would expect that the structure of the product that we would get from this would look something like this. I'm just running out of room. Is it okay if I turn this? I'm going to put my silyl ether over here. SiO, is that okay? Just because I'm running out of room. And here's our new carbon-carbon bond that we would form. There would be 2 ethyl groups and an OH. And probably you all see what I did there. The reason I picked this ketone in particular is because it's symmetrical, and so I don't need to worry about stereochemistry. Ha ha, you probably all see what I did there. So anyway, at this point, we can deprotect, but I do want to point out that this silyl ether over here is an example of what we call a protecting group. Which in this particular case is a silyl ether, S-I-L-Y-L ether. And there are other protecting groups for alcohols also that we could have used. There are other silyl ethers. You can also use tert-butyl dimethyl chloride. That's a pretty common one. Phenyl dimethyl chloride is a thing. Triisopropyl silyl chloride is a thing. And they just vary in terms of how robust they are. But you can, in general, remove silyl ethers a few different ways. One method is to use just dilute aqueous acid. That's one way that we'll do it. Another way is to use a fluoride salt, like sodium fluoride or lithium fluoride, or tetrabutyl ammonium fluoride, if that's your thing on that particular day. The reason is that fluorine and silicon really, really, really like each other. The silicon-fluorine bond is probably the strongest covalent bond there is. So you would get something with a silicon-fluorine bond, and as long as there's a protic solvent around, generally those are done with water around, then you'll put the proton back on. And this, indeed, the same thing would happen over here. And that will give us our alcohol back. We've now deprotected that functional group. And so we would get this compound out at the end. So this is just one example. And you'll see other ways of protecting and deprotecting and reasons or situations when you would want to in the OWL assignment. But I just wanted to get you guys used to the idea, first of all, of incompatible functional groups, and secondly, of protecting those functional groups in those cases. We'll learn other protection and deprotection sequences next term. Like I said, we're not doing it yet. You're not responsible for it yet, but later on we'll learn how to protect ketones and aldehydes, for instance. But this is, I just for now want to get this idea of protecting groups in your mind. That's a good enough place to start. And that's good because I'm out of time anyway. So I guess I will see you all on Wednesday.